let's see. Sorry about the abrupt end of the stream. Someone was knocking at my door, so I have to attend it. Rather than stopping the video, I just mistakenly entered the stream. So let's continue where we left. So we were looking at this residual connection. So how will it work? Because treating back progression, so wouldn't x just vanish because we can't differentiate x in terms of this, right? So how is it good? So if you differentiate in terms of weight, this will vanish, right? So how do you differentiate residual connection? So what do we do? Let's take the line here. How is it even helpful? So doing differentiation. The overall weight shifts, right? So let's use Gemini. So in residual connection, isn't the gradient of fx plus x just f dash x? So the residual input gets differentiated, the value just decreases to 0. So how is it even helpful in residual connection? Because the gradient becomes 0 and it doesn't even affect the weights. Show me this differentiation in terms of weights. the so this term already has, so this term looks like this, right? So dl by dx should look like dy by dx. Okay, it's dy by dx. So this term already contains that extra term, right? So before residual connection it didn't have that. So what you are trying to do is, so if y equal to fx plus x and dl by dw equal to dl by dy dy by dw. So plus into d fx plus x by dw. Is 0, right? But I don't understand this. Why is it? Can you show me in differentiation term how the additive term uh, passes through the lower layer in residual connection? So this one weighted layer, then it passes through another weighted layer and bias comes here at last. Okay, so say in layer 1 x plus e, then we apply value, and it also passes through w. Then in layer 2 we add x to this layer 1 element, layer 1 output. Now if we differentiate L2 with respect dy, dw, L1 is layer after that. So at the end, when we differentiate x of L in also, this gradient, this layer gradient is traveling all the way till the last layer. Previously we didn't had this term, we only had this term. So as we move down layers, it keep decreasing. That's why it has more information. Okay, more information. So this is how it works, right? Okay, so if we have, so x and w before, x plus f2 f of x comma w1 w2. So when we differentiate in terms of, we get y, right? So and y is passed into loss function dl by dy dw equal to say w1 by dl by dy. Y differentiate in L2 value changes, L2 how much is L1 changing in L1 W1. So this y, this gives me dl by dy to x plus value of another layer, isn't it L1? Okay. So it travels through. Now I get it. What it's trying to do. Why is it taking as 72 degrees? It's because of the stream, but it doesn't usually happens that way. Something wrong. Okay, let's go. So we look at residual connection. So what the residual connection does, it passes the gradient loss gradient directly to the lower layers. So it doesn't get vanish along the way. So that allow us to train deeper layers. So if you have a deeper layer, the residual connection doesn't get small. I think because of that, lower layer models have less error because the gradient doesn't vanish, doesn't because they have lower layers, lower number of layers, because of which the gradient, when it reaches the last layer compared to 54 layer, the 24 layer will have a larger value. So the residual connection, what it does, it is so what it does, it tries to skip some connection and pass the loss to lower layers directly. That's pretty nice. So they will know how the loss changes compared to their weight, and while keeping keeping the information of the middle while keeping the rate of change in terms of middle layer too. mm, that's really clever. Okay, so now we know about the residual connection. So something else, this is the residual function. So now we have example network of image, and left is pgg19 flops as reference. Middle plane is 32 parameter layer, 34 parameter layer, 6.0 and residual. So the residual connection skips two layer and passes the data of the input directly to different layers. So it skips the layer. What does the dot date? What do you mean with the dotted connection? So VG19 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 18 19. So it has three fully connected layer. It is a pooling layer. 32 plane layer. So it takes the image. It has a 3 into 3 convolutional matrix, which are comprising 64 different kernels versus two different. Okay, output size is 224. I have to look at VGG network. So this is the convolutional layer. Input size 56 and 56. Layer 7 to 6, 64 strike 2. Convol layer name in convol 1. We take this in convol x. We took 2x, 3x, 5x. Okay. Flops. So architecture of imaginary building block are shown in the bracket. Which the number of blocks take down sample 5 1. So I have to understand this table. Before that I have to understand VGG16 and all this residual connection, how all that works. So let's see how VGG16 different model works. To look at how to read this, then after that we'll look at these different ResNet layers, EN inspection, prelude, VGG, LessNet. We look at different models. Method, what are all these terms? FitNet, highway, ResNet, layers. Then we have to look at all this graph, error rate graph, MMP at 5 to 6. Okay. Let's first start with VG19. What is this? How does it work? How does it look? why is my let me stop the stream now. I don't know what's happening to my laptop, but the fan are the fan of my laptop is running pretty fast. The fan it's using a lot of noise, but I don't think the CPU is making that much noise. What happens to it sometimes? I don't even know. Okay, I think it fix. Okay, I think now it's working. So let's look at VGG 16, 19, VGGNet, VGG. Let us understand what is VGG even mean. VGG.
Greetings, fellow learners. In this video, we are going to take a look at VGGNet. This was the state of the art for object recognition in 2014, so we're going to take a look at it. So object recognition, this is the problem where we take an image and then the output is a category of said image. And in 2012, AlexNet was the state of the art for object recognition. And this was mostly because of the rise of the internet and hence the creation of large data sets like ImageNet and GPU availability, like NVIDIA's GeForce released in 1999, but became more prevalent later in the 2000s. But can we do better here? Now, one way to think about increasing performance is to increase network depth. And so researchers at the Visual Geometry Group at the University of Oxford thus created this suite of architectures with 11 to 19 layers. So we have A, this is ALRN, B, C, D, and E. Each of these are different network configurations. And this suite of networks became known as VGGNet. So the main contribution was based on the following. During a convolution operation, we can approximate large filters with smaller 3x3 convolutions. And specifically, a 5x5 convolution will have the same receptive field as two 3x3 convolutions, and a 7x7 convolution will have the same receptive field as three 3x3 convolutions.
What? How?
Now, to see exactly like how this is the case, let's illustrate this with an example using the one-dimensional case. So here we have an input, which is like a one-dimensional signal. Each of these are like floating point values. And let's say the size of the input is 7. Next, we just have a size 5 filter, which is one-dimensional, that looks like this. And if you apply convolution, you'll see that first, this first number over here is going to be the sum of products of these 5 elements over here. Then you'll get this one floating point value. And then we just keep sliding the window. The cell over here has a receptive field of 5. So what that means is that this over here, this floating point number, is some function of these 5 inputs. Similarly, this second one is a function of these 5 inputs. And this third one is a function of these 5 inputs. And also, each cell is a linear function of the 5 inputs because it's just a sum of products. No nonlinearities. Now, let's look at the second case where we use 3x3 filters. So we have the same input. Now, we'll use a 3x1 filter over here in order to output. Now, each output cell has a receptive field of 3, so it's just a function, a linear function of 3 inputs. Now, let's say that we use another 3x1 filter, right? And once we do this, let's say we take the sum of products of, these over here, you'll get this output. Similarly, you can slide the window to get the total output. Now, what's interesting here is that this second output is actually going to be a linear function of 5 input cells over here. So it's like a function of these 3, which is in turn a function of these 5.
Okay.
So this is exactly just like the 5x1 case. So you can kind of see that, hence, the receptive field of the 5x1 filter is the same as the receptive field of these 2 3x1 filters. So hope that makes sense. And we can even extend this if we add another 3x1 filter right over here. We take the sum of products, you'll get this single final output value. And this output value is going to be a linear function of these 7 inputs. So each output cell is a linear function of 7 input cells, and this is similar to a single 7x1 convolution. So I hope you can see how now a 7x1 convolution can kind of be represented by a sequence of 3 of these 3x1 filters. And we would just need to extend this in 2 dimensions for the case that I just mentioned. Hence, during a convolution operation, we can approximate larger filters with smaller 3x3 convolutions. Now, why would we want to do this though? So first, it decreases the number of learnable parameters. And second, it increases the number of layers, which increases the ability to add ReLUs after each of those layers, which increases the discriminative power of the network.
So we have less learnable parameters. Yeah, we have 3 plus 3, right? 5 is 525, 30 and 9, 9, 18. Okay, that has 18, but a single 5 plus 5 layer has 25 different weights. Let's increase layers. increases ReLU, increases discriminating power. If you have more nonlinearity, we can operate okay.
So let's look at exactly what we mean and how this actually happens with an example. So let's say that we want to, in our case one, take a 5x5 convolution and we want to apply it to like a tensor with 64 channels. The 64 is the depth over here. And this, we want to transform it into another tensor with 128 channels. So in order to do this operation, we would use like one of the filters would be like 5x5 cross like 64. We would apply a convolution operation by sliding it across this entire tensor. We'll get one of these 32 cross 32 feature maps. And then we need to use 128 such filters in order to get this full feature map over here. And hence the number of parameters is going to be 5 times 5 times 64, which is the number of input channels, times 128, the number of output channels. And you get 204,800 learnable parameters with this single 5x5 convolution. 8, number of output channels, and you get 204,800 learnable parameters with this single 5x5 convolution. Now let's move on to the second case where we mention we have a sequence of two 3x3 convolutions. And let's say that from 64 channels, we want to go to 32 channels, kind of as a bottleneck, and then transform it to 128 channels. In doing so, the number of parameters incurred is 3 times 3 times 64 times 32 plus 3 times 3 times 32 times 128, which is 55,296 learnable parameters. And the number of parameters here has certainly decreased by like 4x compared to the previous case. And the second point that I mentioned before was that we can now add two nonlinearities, two ReLUs over here versus like one in the case of like a 5x5 convolution. And this is to make the network more discriminative, more powerful. And so I hope those 2 points make sense. So replacing these larger convolutions, the 5x5 convolutions and 11x11 convolutions from AlexNet, we can just replace it with like 3x3 convolutions, and we can then create deeper networks that are more performant.
Okay.
And when I say more performant, I'm looking at like the ILS VRC competition in 2014. And if you look at the different categories here and you scroll down, what you're going to see is that for object like classification and localization, VGGNet came on top. So it's performant. Now, in order to put these numbers in perspective, I've also created some code. So let's take a look at that. So here's some code that's basically going to train a simplified version of a VGG network and simplified version of an AlexNet, and then compare the two. So right here, we're going to train this on the Cypher10 dataset, which is essentially going to be a object recognition dataset with 10 classification outputs. Then we have the code for training and evaluation. And then we create an architecture for AlexNet. It's a simplified architecture from the original one, but it has the same ideas. So we first have, let's say we take the input image, and then we transform it with a 7x7 filter, or a 7x7 convolution to create 64 output channels. And then the second convolution block, 64 to 193, exact network over here, what we're going to do is we're going to replace the 7x7 convolutions with a sequence of 3x3 convolutions. And we're going to replace the 5x5 convolutions. So we transform 5x5 change, and this is just to give you the idea of comparison. So if we compare the number of parameters, we see that this VGGNet now has like half the number of parameters as AlexNet. Yet when you actually train the network on the exact same amount of data with the same configuration parameters for the same amount of time, you're going to get slightly even better performance in the VGGNet case. So I hope this VGGNet architecture is with like elements. Have you been paying attention? Let's quiz you to find out. Which of the following is true about VGGNet? A, it uses stacks of 3x3 convolutions with 2x2 max poolings. B, it introduces residual or skip connections. C, the network is sparsely connected and hence has a lower parameter count. Or D, it removes fully connected layers in the original model. Your reasoning down below and let's have a discussion. And at this VGGNet, the what, the why, and the how. So we started with the fact that AlexNet was the state of the art for object recognition, and we tried to see how we could do better. VGGNet actually does this by increasing the network depth. And specifically, it replaces larger convolutions with much smaller 3x3 convolutions. And so that's like a 5x5 convolution will have the same receptive field as two 3x3 convolutions, and a 7x7 convolution will have the same receptive field as three 3x3 convolutions. And we also see how this is kind of proved out with a simple example. We also mentioned the reasons for potentially wanting to do this, where it decreases the number of learnable parameters while increasing layers, increasing relu activations, hence increasing the discriminative power of the network. We then saw exactly this in code where we compared the AlexNet architecture, a simple much are watching all the resources and the code.
हाय गाइस, माय नेम इज़ नितिश एंड यू आर वेलकम टू कैंपस एक्स। इस वीडियो में भी हम लोग अपना डीप लर्निंग प्लेलिस्ट कंटिन्यू करेंगे। अभी तक हमने डीप लर्निंग में CNN के अंदर दो चीज़ें पढ़ी। फर्स्ट ऑफ ऑल CNN आर्किटेक्चर्स कैसे काम करते हैं, और हमने फिर खुद का CNN आर्किटेक्चर बना करके इमेज क्लासिफिकेशन के ऊपर भी थोड़ा काम किया। आज का वीडियो थोड़ा अलग है बिकॉज आज की वीडियो में मैं आपके साथ
VGG16, right? So what I understand is the VGG16 has 3 into 3 convolutional, 3 to 3 into 64 kernels. After that we use a pooling layer. We use a pooling layer. We increase the number of kernels again. So this goes on till we have the fully connected layer 1000. Okay, it takes this number of flops. So now I have to look at what are flops written and all that. I have to understand some of the terms here. What does all this means? Convolution 24, convolution 3x, convolution 4x, right? So I have to revise some of my CNN topics. Okay, what a stride and all that. I have to look at it, all that data set. So I think I will stop the stream here. I will do some background study regarding all that. Then I will again be back. Then I will start the stream. Then I will look into all this today and again stream tomorrow from where I left out and try to understand this paper. So my goal is to implement this paper after I understand all this, and then again go through the whole paper, read the paper and understand. Then I want to do this for 2 to 3 papers to means implement implement a network, read and implement an paper. So that will